Hello everyone, welcome to my channel. In this series of videos, I'm going to dive into one of the greatest achievements of human thought, which is the discovery of quantum physics. Now, before we start, there's a lot to talk about when it comes to quantum physics, both from scientific point of view, from the historical developments, and from the application point of view. What I would be focused on in this series of lectures is to teach, let's say, second or third year students in physics, as well as even a general wider audience, the methods of quantum physics, what it really talks about. Anywhere throughout the lectures, if we encounter some, technical mathematical problems, I would pause and I would try to open up a short interlude in order to discuss the math and then get you prepared to understand the physics. I believe that this course would be useful, as I said, not only for students that are majoring in physics, but I would try to discuss especially the concepts apart from the mathematics parts for a more general and wider audience. So I will start by not looking through the historical development of quantum physics. In fact, I should just mention a couple of words here. It was the opening years of the 20th century in which a series of experiments showed up in which physicists were not be able to describe them in terms of back then well-known laws of physics, which were mainly classical electrodynamics by Maxwell and Newtonian mechanics by Sir Isaac Newton. So for over 200 years, classical physics was, and it actually demonstrated that it was sufficient to tackle the problems and explain most of the fundamental not fundamental really, but most of the phenomena that we see around in the world. And there weren't any problems until right up the turning years of the century, especially speaking 1899, 1900. It started to, what we say, cracks started to, appear in the great enterprise of physics. And scientists, well, they love mysteries. No matter how beautiful a theory is, no matter how many different phenomena it can explain, but once you encounter an observation or an experiment in which the established theories cannot describe, no matter how beautiful they are, you must admit and accept the fact that it is wrong, and we have to put it aside. Or in the best case, we would have to generalize it to cover the newer realms. Now, the sole judge of scientific truth is experiment. So that is really the point in which, or that is, I would say, the red line in which you can, come up with your theories. So the theories are valid as long as experiment verifies or validates them. Now, quantum physics is very, very radical in the sense that it not only altered the theories that we had in classical physics, but it also altered the human thought. It also, taught us to rethink the most fundamental, concepts that we take for granted. And it's a very, very interesting and at the same time weird theory. And I would like to start the course on quantum physics by looking into one of the mysteries of quantum physics and one of the interesting parts of quantum physics, which is about quantum indeterminacy and the problem of measurement. So we will look into Schrodinger's equation, but before that, I would just like to remind you what is the program of classical mechanics. I mean, ordinary mechanics or classical mechanics or Newtonian mechanics, whichever you want to call it, is basically essentially a deterministic theory. What it means is that, what all of classical mechanics is attempting to do is to solve a simple problem. And the problem is, if I know the forces or the interactions of the environment on some given particle or body or object, I would like to see how I can find the future of that object. In this case, the future position of the object. So here I've showed a very simple or simplified case here. So let's say I have an object that we show it by this particle m here, this point m. This m is supposed to represent its mass, and let's say it's constrained without any loss of generality to move along the horizontal axis, right? And let's say this object is subject to some kind of force. Force is applied to it, which can be, in general, a function of position and time. Now, as this force is applied to this object, well, obviously, the object will start to accelerate, and it would, go to another position in general. And we want to see how we can find that position. And the answer to that is Newton's second law. In his work Principia, Newton introduced his second law of motion, and he said that if I know what the force is, in principle, I should be able to calculate the acceleration of the object, and if I know the acceleration of the object, I can find its velocity through integral calculus, and then its position at any given time. So this is a portrait of Sir Isaac Newton. To many scientists and physicists, he is the greatest and brightest human being to ever have walked on this planet. And I will try to make you appreciate how important this, how brilliant this man was, especially his masterpiece Principia. Through only a set of simple, propositions, simple assumptions, and basic rules, he built the entire, or laid the foundation of the entire science of mechanics. And as I said, his theory survived for over 200 years before. I mean, it took quantum mechanics and special theory of relativity to come and, in a way, overthrow it. But and this apple is obviously represents the story that Newton was, sitting underneath an apple tree in his home, and suddenly an apple fell down, and it inspired him to come up with the law of universal gravitation. In our course in classical mechanics, we'll look more into, in detail more into Newton's work. So if I know that force, if I know that interaction, and if I know the initial conditions of my object, namely where the object was at some given moment of time and how fast it was moving, then through Newton's second law, I can, in principle, calculate for sure where the object will be in the future, even where the object was in the past. In other words, Newtonian mechanics is completely deterministic. So it's in Newtonian physics, the universe is like a grand clock. Okay, so you set the clock and it works for itself, and you can predict what it would do, and you can do that for any amount of time in the future or in the past. So that's the power, by the way, of classical physics. It gives us stability in our predictions. So if you find this position of the object at any time, then you can look into any dynamical variable of interest, such as the velocity of a particle, which we know it's the time derivative of its position. So if I know the equation of motion, if I know how the particle changes its position in time, and I know the mathematical format function of it, I can just take a simple derivative to find its velocity. If I know its velocity, I can calculate another dynamical variable, which is its momentum, mass times the velocity. I can also calculate, think of the kinetic energy of the particle in classical physics as 1/2 mass times the square of the velocity, and countless other dynamical variables. So this x of t is actually very important. But how can we find x of t? And as I said, all we have to do is to solve Newton's second law. So Newton, he gave this to humanity. He gave a simple rule to find where objects are. But the only thing that we must make sure is to know what this force is. So if I know what this force really is, then I can solve this equation for A and find the acceleration, and from the acceleration find velocity and position. Now, in quantum physics, we are looking into conservative systems. In fact, in the microscopic realm, which is the realm in which quantum shows itself, it reveals itself in a way, as in the microscopic realm, the subatomic and atomic realm. Systems are conservative. What do we mean by that? Is that there are no dissipative forces, energy is conserved, the interactions are clean. And as we know from classical physics, any conservative force can be driven or can be derived from an interaction potential energy. Now, in this case, if our force is one-dimensional along the x-axis, as I showed, the potential energy v, if I take its partial derivative with respect to the spatial coordinate with a negative sign, that will give me the force. Of course, in classical physics, we have magnetic forces, which depend on speed or velocity, and thereby they are not conservative. Remember, conservative forces are forces that depend on position, not on speed. So magnetic forces are an exception. But anyway, in this context, we are not going to worry about magnetic forces. And the reason is we are going to discuss in this series of lectures the classical, not classical, non-relativistic quantum physics. In other words, we're going to talk about speeds that are not comparable at all with the speed of light. So when speeds approach the speed of light, we have to replace these theories with a new one, which is done by Paul Dirac. But for the meantime, we're just looking at a simplified version of quantum theory, which is within the non-relativistic realm. So here's Newton's second law. I just replaced ma by what it is. A is the second derivative of position, it's the acceleration. And for f, we can show it by the negative gradient of a potential, interaction potential. So this is the equation that I must solve. As you can see, it's a second order differential equation. Of course, in high school, you probably haven't seen it, but in disciplines of engineering and physics and first and second years undergraduate studies, you would know how to solve second order differential equations. Right now, I'm not going to look into the details. You can find the details of solutions of this equation for various cases and in different lectures that I would be giving in the future. Well, when you solve this, since it's a second order equation, you have to specify two constants. And two constants, which we call here the initial conditions or the boundary conditions, are the position and the velocity of the object at the moment you are taking as the origin of time. So if I know the position and velocity of an object at some point in time, not necessarily zero at any point in time, if I know these two pieces of data and I also know how to solve this equation, then I can predict where the particle for sure definitely would be at any future time. That is the power of Newtonian physics. So speaking of power of Newtonian physics, well, here I just show you a couple of examples of what this theory led us eventually as a human species. So here you see all of these magnificent, accomplishments that we humans were capable of, thanks to Sir Isaac Newton's work. That's why I said that he is, without doubt, one of the greatest people that ever walked on the surface of the earth. Before Newton, we never had these massive engineering projects, but after Newton, all of them became, accessible to us. All of them were realized. So here you see the Golden Gate Bridge in San Francisco. To hold such a huge construct, you must know the laws of statics, which follow from Newton's laws in static equilibrium. In order to build giant skyscrapers like the skyline here in Manhattan, New York, you also need to know the knowledge of statics and civil engineering, which they are all derived from simply Newton's second law of motion. Here we have a famous picture of Buzz Aldrin, one of the astronauts that walked on the surface of the moon. Of course, just to let you know, the picture was taken by Neil Armstrong, the first man to set foot on the moon. And what I'm trying to say here is that in order to send a man on the moon, all we needed was Newton's second law, or Newton's laws of motion in general, right? So we didn't need any weird, scientific theory in order to calculate and send people safely to the moon and return them back. This is a picture of a Boeing 747. It's one of the greatest accomplishments of our species. Think of this huge aircraft, just floating in air. Again, the laws of physics, the laws of classical physics is all we need to, manufacture or make these things work. And here on this corner here, you can see the spaceship Voyager, which was launched in the 1970s. Right now, it's past the boundaries of our solar system. And the trajectory of this spaceship and the success of its mission were all, possible because of Newton's equations of motion. So no doubt that classical physics really works. But there were areas, as I said in the beginning of the lecture, in which classical physics started to break down. Now, that's where we come up with the quantum theory of physics. Now, in quantum mechanics, unlike classical mechanics, what we are interested in is not the position of a particle at some moment of time, but the state of the particle, which we show by a weird function, which we call the wave function. This is shown by the Greek letter capital psi, and it is a multivariable function. Now, in one dimension, there will be a function of space and time. So the state of the particle is described by the so-called wave function. Now, how do we find the wave function? Just like Newton's second law with the appropriate boundary conditions led us to find the position of a particle as a function of time, for the wave function, if we want to find it, we have to use another equation. That equation is called Schrodinger's equation, and it's given here. It looks rather complex, and this is, trust me, a simplified version of it. We'll discuss what each term is shortly, but this is attributed to Erwin Schrödinger, the Austrian physicist that at the age of 38 came up with this equation. This is Schrödinger's wave equation written in one dimension. So when I look into this equation, I see multiple, quantities appearing here. Psi is the wave function. X and t are the independent variables, which are position and time. V is the interaction potential energy, and in the realm of quantum physics, or generally in atomic physics and nuclear physics, we tend not to talk about forces. We tend to think in terms of energies. So you don't see a force appearing here. It's just the potential, the interaction potential appearing. This first term, you can think of it as a kinetic energy term. Later we'll see why it's that, but it involves the mass of the particle and a constant here, h bar, and another constant here, I. So what are these? Well, now here's the Schrödinger's famous cat. We'll get to that later. But yeah, I is the square root of -1, the imaginary unit, and h bar is called the reduced Planck's constant. Planck's constant is h, and it is the constant that appears in quantum physics. And h bar is of the order of 10 to the minus 34 joules second, which is the unit of action in SI units. And Planck, we think of him as the one of the founding fathers, or in fact, he's the father of quantum physics. He tried to describe the spectrum of the black body radiation, one of those problems that I said or mentioned earlier that showed the inaccuracy of classical physics. And he actually came up with a brilliant idea of considering energy to be quantized, not a continuous stream, but a quantized stream of particles with this constant here, Planck's constant. Okay, back to this picture. This is Schrödinger's cat. It's a sort of like, think of it as a thought experiment. We'll get back to this throughout the course, what this is, but this actually has philosophical implications. So here, just to let you know what's going on, imagine you have a cat that is stranded in a box. You're not allowed to look into the box. The box contains some radioactive material, and upon decay of the radioactive material, it triggers, let's say, a hammer, which itself breaks a glass of poison, and then if that happens, the cat dies. Now, since in quantum physics, we'll see later on, in quantum physics, there is no 100% prediction of an outcome of a measurement. So we're talking about probabilities there. We don't know. We really don't know, in a sense, when this, for instance, radioactivity is going to happen. I mean, those of you who know a little bit about nuclear physics, you would know that we have unstable, nuclei such as uranium, those heavy nuclei here, that they disintegrate over time through radiation. We call it radioactivity. But the moment in which, let's say, a given nucleus emits some radiation, that is not known for all. It's a complete random and spontaneous process. It can happen anytime. Okay, it can happen right now, or it can happen in 100 million years. Okay, so it's a random thing. It's a spontaneous, random by its nature. So we really don't know before looking into this box to see if the cat is really alive or dead. But once you open the box, then one of the two possible outcomes will show up. We'll later discuss about this. Anyway, although we say that quantum physics or quantum mechanics is indeterministic, but still Schrodinger's equation has some kind of determinacy embedded into it. And that is, if you look at the equation, it's a first order in terms of time. It's linear in terms of time, let's say. That means that if I know the wave function, remember we're talking about the wave function, not the particle itself. If I know the wave function at some beginning of time or some origin of time or instant of time, if I solve Schrodinger's equation, that can give me the wave function at any future time. But before we end this part here, here in this little chart or table, I just tried to compare the program of classical mechanics and quantum mechanics. In classical mechanics, the fundamental equation would be Newton's law of motion. In quantum mechanics, non-relativistic quantum mechanics, is Schrodinger's equation. Newton's second law, along with the initial conditions, which are the speed and the velocity, the speed and the position of the particle at the beginning of the experiment, give us the position of the particle at any future time. Here, in quantum mechanics, we're not interested in the position of a particle, but we're interested in what we call the wave function of the particle. And the wave function of the particle can evolve according to Schrodinger's equation. All right, so let's see what the wave function itself is. After all, the position of the particle is something we know, we recognize. But what is the wave function? What does it really represent? Now here, I wouldn't say it's an example of a wave-particle duality, but it looks very similar to that. So don't confuse it with wave-particle duality, but think of this little paradox that would appear in your mind right now by considering the fact that a particle, well, is a finite, extended, or even a very tiny object, right? It is either located at somewhere or is it not? Okay, so there are places in which the particle occupies and there are other places in which the particle is not there. So particle is localized in space by its definition. And by the way, when we talk about particles, we not necessarily mean tiny objects, tiny, like dust particles, or we don't necessarily mean it. We have to look into the category or the context in which we are describing the particle. So, for instance, the planet Earth, for instance, can be considered a particle, but obviously not for us. But when we look at it from a faraway distance, let's say in the scale of the solar system, planet Earth, including the other planets as well, and the sun even, they can be considered particles. So it's really the dimensions that matters here. So if the dimensions in the problem are much, much bigger than the the internal dimensions of the object themselves, that object we can consider it as a mass point of the particle. But nevertheless, whether the object is huge or it's small, it still has a finite extent. It is localized. On the other hand, a wave is not localized in space. It spreads out in space. So it doesn't really make sense to talk about where a wave is, right? Is it here? Is it here? Is it here? It's just a wave. It's by its nature, it's an extended and non-localized entity. Now, how come this wave function would represent the state of a particle? That's the point here that I'm trying to talk about. Because after all, if it's a particle, it should be a point, a finite point. If it's a wave, then as it appears to be, and it satisfies the wave equation, then what is this? How can I reconcile this? I mean, it's starting to get weird. Well, there's an answer to it, and the answer is given by Max Born's statistical interpretation of the wave function. Now, it would even get weirder because Max Born came up with a proposal that showed that what we are actually looking at when we're doing a measurement or we're studying a system is the probability of finding a particle, and not the particle itself. So this wave function is actually the amplitude of a probability distribution. So it's a complete mathematical abstract entity. In other words, although psi itself, the wave function itself, is in general a complex function, but the square modulus of it, psi squared, is real and non-negative, because square modulus, from linear algebra is just the complex conjugate of the function multiplied by itself, right? So it will give us a real number, and it's non-negative. And probability is a non-negative real number, right? So Max Born suggested that maybe this psi, whatever it is such that psi squared, the square modulus of it, represents probability. And in order to show this in more detail, let's say I have a particle distribution here, psi squared distribution plotted against the x-axis, and we're looking at it in different locations in space, such as A, B, C, where the psi squared is greater. That according to Born's interpretation, it means that the particle is likely to be found there. So if I make a measurement, it's likely that I can find the particle close to point A here, because the square modulus of the wave function is higher here. On the other hand, if I make a measurement, maybe the particle is less likely, almost zero chance to be found in point B, because psi squared is almost close to zero. Point C, a little bit probable. But anyway, in Max Born's work, this integral, the integral between 2 points in the space in which the wave function is distributed, or the probability function to be more exact is distributed, this integral gives us the probability of finding the particle between these two limits of the integral. So in other words, it's the shaded area here. The shaded area, the bigger it is, the more likely is the particle would be there when we try to look for it. In other words, probability is the area under the graph of psi squared. So the statistical interpretation introduces what is called quantum indeterminacy. This is coming from the probabilistic nature of Born's interpretation. Right? Remember, we talked about a probability distribution. So the particle can be anywhere. You can see here, it can be anywhere, but it's more probable to be here, than here, for instance. Okay, so quantum mechanics doesn't, it's unlike classical physics, it doesn't give us a solid answer to where we can find the particle. It just talks about probabilities. So here, part of it is behind my my image here. It says the outcome of a certain measurement to find particles is uncertain. All quantum physics gives us is statistical information about the possible results. All right, so in light of this, there are three different schools of thought that I've tried to point out. The first one, which is advocated by this famous gentleman, Albert Einstein, is the realist position. Einstein truly believed that quantum physics was not a good theory, was not a complete theory. He thought, and his followers, or people that thought like him, thought that prior to the measurement, before finding where the particle is, the particle is actually somewhere. It is at a given place. It's just that we don't have enough knowledge to find it, or quantum physics doesn't give us enough information to find it. In other words, people like Einstein thought that there must be hidden variables that must be introduced to quantum physics in order to make it complete. Because after all, what is good of a scientific theory if it doesn't allow us to predict solid results? So Einstein really thought like, let's say, Newton, right? Or all the physics before quantum mechanics, actually. They were all deterministic. So Einstein advocated that it's just because we don't have enough information. That is why we cannot predict where the particle would be. That doesn't tell us anything about the particle's existence. It is there, it's just that we are ignorant. So indeterminacy is not a fact of nature, but a reflection of our ignorance. Opposed to Einstein, there were another class of physicists, Niels Bohr as one of them, that advocated what is called now the orthodox position, or the Copenhagen interpretation of quantum indeterminacy. What do they say? Now, this is where things get really weird. In the orthodox position, it is believed that the particle is really nowhere and everywhere at the same time, okay? It's very weird. It's the act of measurement that forces the particle to take a stand or take a position. So before the measurement, the particle is everywhere, okay? It's not that our theory is incomplete. It's really everywhere. But then when or it's nowhere at all. So it depends on how you look at it. So when you perform the measurement, something happens and causes the particle to take a position. Some even think of it more radically and say observations not only cause the particle to take a position, but even produce the particle. Think of it a little bit. It's really weird. When I even think about this, sometimes I get goosebumps because think of, here I've taken a quote from David Merman, who was another brilliant physicist. He said, really, do you think that there's no moon if no one looks at it? I mean, this is what the orthodox position is telling us. It's telling us that there is nothing there, but once you attempt to look, then something happens. So it's the fact that observation is actually influencing nature at the fundamental level. We'll get back to the orthodox position. As I said, there were many physicists that followed Niels Bohr, including Werner Heisenberg. All of them, they actually advocated this school of thought. Now, there were endless nights in which Einstein and Bohr were debating with each other. And we all know Einstein was one of the most smartest people or the smartest scientists that there was ever been. And he always came up with some kind of a loophole, thought of a loophole in quantum physics, with some kind of a quantum riddle, and handed it to Bohr and asked Bohr to say, you see, at this point, quantum physics is failing. And Bohr went and thought about it, and the next day he came and answered Einstein's. So they had this debate over and over and over. This is a picture, I think it's taken from Paul Ehrenfest, another great physicist's house, and they were actually talking about the metaphysical implications of quantum physics, what philosophically it means, and so you can see the clash of a realist with a orthodox here, and And this was happening in Paul Ehrenfest's house, and Ehrenfest, unfortunately, he committed suicide because some believe that he couldn't get his mind around accepting or absorbing all of these, very heavy thoughts that challenge everything, challenge all the way that we've been thinking before. And so some people couldn't just take it, including Paul Ehrenfest. But let's say if I want to just in simple words mention one of the famous, questions and answers between Einstein and Bohr, is that Einstein thought that, he, as I said, he thought in the Newtonian way, and he was a realist. He said that God does not play dice with the universe. What he meant was, obviously, scientists, the majority of them don't believe in a God. Certainly, they don't. Certainly they don't believe in a Abrahamic God, someone that answers to prayers, or you make sacrifices for him, or cares about what you do, what you eat, who you sleep with. So the scientists really, the ones that are spiritual, they believe in God in a Spinozan way. And Einstein was one of them. So when he's talking about God, he's actually talking about the laws of physics. And he says that, God doesn't play dice because he wants everything to be clean and predetermined. But on the other hand, Bohr came with a wise answer. He said that, who are we to tell how God to govern the universe? So here you have a picture of the Hubble's deep field image of the universe, and here we have a pair of dice, and you see that we don't know the outcome of the dice before we, play it. So this was an interesting epoch in the history of quantum mechanics that took place. And finally, the third school of thought on quantum indeterminacy is the agnostic position. Now, it might sound silly, but agnostics refuse to even answer. And they say, okay, who cares whether there was a particle before the measurement or whether there wasn't a particle before the measurement? Who cares whether the measurement produces a particle or not? I mean, does it really make sense to talk about the outcome of an experiment without doing the experiment? So who cares about what's going on before it? So they refuse to answer. In other words, it doesn't make sense to talk about the position of a particle prior to measurement, as measurement is how one finds a particle in the first place. It is in fact metaphysics in the projective sense of the world, to worry about something that cannot be tested by its nature. So they thought that these discussions were, about metaphysics, and it's not a scientist's job to think about things that cannot be essentially tested. Wolfgang Pauli, we know him from Pauli's exclusion principle, one of the great minds in physics and quantum physics, says that one should no more rack one's brain about the problem of whether something one cannot know anything about exists all the same than about the ancient question of how many angels are able to sit on the point of a needle. So this was an agnostic position. Now, in 1927, there's a famous picture of the Fifth Solvay Conference in physics. And here we see all these great minds gathered together. I mean, this is a historical moment in the history of science. You see, for instance, Einstein here, Lorentz, you see Heisenberg here, you see Schrödinger, Marie Curie here, Max Planck. I think I can also find, here's, let's say, Max Born. I think he's also here. Max Born. Yeah, here's Niels Bohr. Dorwell Brillouin here, for those who have studied solid-state physics, is familiar. We also see de Broglie here, and Dirac. Here's Dirac. So many of these great scientists, they gathered together, and in 1927 they established quantum physics. So look, quantum mechanics was born in 1900, and it took more than a quarter of a century for the physics community to accept it. Of course, Einstein was the main figure that until the end of his life, he didn't even, accept it. But then it was after this meeting, that people took quantum physics seriously in the scientific community, and later on, it found its way in textbooks. So, which one will it be? Is the realist position, the orthodox position, or the agnostic position the right standing point about quantum physics? And here I've shown the answer, okay? It makes an observable difference whether the particle had a precise position prior to the experiment. So experiment, at the end of the day, that was done by the work of this gentleman here, John Bell. In 1964, he came up with an experiment that showed that it was actually the Copenhagen interpretation that was the correct viewpoint. And by that, he ruled out all the other schools of thought. So the realist position, no matter how weird it was, the Copenhagen or the orthodox position was the correct interpretation of quantum physics. Experiments, which, as I earlier said, they are the sole judge of scientific truth, have decisively confirmed the orthodox interpretation. The measurement does indeed create the result. Welcome to the bizarre world of quantum mechanics. Pause a little bit and think about it. The orthodox position was the most radical position, because the agnostic position said, well, simply, I don't know. They refused to answer. The realist position said that our knowledge was incomplete. But the orthodox position said that it is nature itself that is acting completely weird. So when you're measuring something, you're actually producing it in this quantum scale, of course. So let's go back to our wave function here, or the probability distribution to be more exact. Let's say I make a measurement, right? And I find the particle to be at C. It can still be at C, it has a finite probability. So maybe I'm lucky enough to find it at C. So once I perform the measurement, immediately during the measurement, or the measurement causes the wave function to collapse, and it takes a sharp peak at point C. So it means everywhere else it's 0, and it would be around point C, right? So that's how I know the particle was at C, okay? Because if it wasn't, if it's not at C, it will have some finite amplitude here or here, okay? So once I make a measurement and I find the particle to be in a particular position, then the wave function collapses during that measurement to that position. Now imagine I take a second measurement. If I do this immediately after the first measurement, I will reproduce the same result. Because after all, what's good of a measurement if you cannot reproduce it, right? So for instance, let's talk in terms of classically. Let's say I measure the gravitational acceleration of the Earth to be 9.83, let's say, for instance, at some location. If I come back later and I measure it again, if I end up with some other value, that'll make me confused. I cannot end up at different values with the same, measurement, right? So that's what we would like. We would like our experiments to be, reproducible and yield the same result. So if I do the measurement immediately after the first measurement, I would end up with the same result. Okay, nothing very weird about it. So repeated measurement must return the same value should it be performed right after the first measurement. Now, let's say after the first measurement, which collapses the wave function around C and forces it to make a stand at C, then I don't make any other measurement. I just look away. I don't make a measurement. After a while, the wave function would gradually spread out. So every time I make a measurement, I get a spike. But if I don't make a measurement, the wave function or the probability distribution will spread. Why is this so? It spreads according to Schrodinger's equation. In later videos, we will actually calculate and show to you why this happens. So this is a smooth spreading out, gradual spreading out of the wave function. But then once again, when I measure it, and this time I might find it at B. So if the measurements are not done in short time periods, depends on really the experiment, then you might end up with multiple results. But if you immediately do the measurements, you would end up with the same results. So if the system is left on its own, then the probability distribution will start to spread out according to Schrodinger's equation. Okay. So here we are talking about two distinct physical processes in quantum mechanics. The ordinary processes, which are like these ones, in which the wave function smoothly evolves under Schrodinger. Remember, microscopic systems are very elegant. They are extremely prone to external perturbations. So as long as you keep those perturbation minimums or make them zero, that means even not looking at them, the wave function would smoothly evolve according to Schrodinger's equation. But then, if you interact with the system, if you do a measurement, then we have a sudden discontinuous collapse of the wave function, which are the second type of processes. So the problem of measurement, what are the interpretations? And this is the last part of this lecture here. What are the interpretations of the measurement problem in quantum physics? Well, what does a measurement really do? Well, it depends on who you ask, really, at the end of the day. So if you ask Niels Bohr, he would say a measurement involves an interaction between a macroscopic system, like a microscope or a human being or whatever, with a microscopic system, an atomic system. If you ask Heisenberg, he says that a measurement leaves a permanent record on the system. It changes it forever. If you ask Wigner, he even made a more radical assumption. He said that a measurement is linked to the interaction of a conscious observer. That means if he related the problem of measurement to consciousness. There are even weirder viewpoints. One of the ones that are mostly celebrated is the many worlds interpretation of quantum physics. In fact, they say if you have a probability distribution and you make a measurement, so you get one result, that doesn't mean the wave function has collapsed to that point. What it simply means is that all possible outcomes of a measurement, all of them, are realized, but you just live in a world in which a particular result shows itself to you. In other words, what this many worlds interpretation tells us is that every time you make a quantum measurement, you are splitting the world into all possible parallel worlds in which all other possible outcomes can be realized in. In a simpler language, let's talk about the Schrodinger's cat again. So you see, once you make the measurement, let's say you open the box, you find that the cat is dead. That doesn't mean that the wave function of the cat has collapsed to the dead state. What it simply means is that at the moment of measurement, you split the universe into two parts, two parallel parts. You copied the universe, but with a slight difference. One universe, the cat is alive in it, and you opened the box and you found it alive, and in another universe, you found the cat to be dead. This is the many worlds interpretation of quantum physics. But at the end of the day, these all fall into the philosophical realm. We cannot test these ideas, no matter how strange they are or how fun they might look like. But as I said, you're free to choose any way to interpret the results of a measurement. But always remember that science is about knowledge, is about truth, it's about verified experimental truth. And the orthodox or Copenhagen interpretation of statistical of Born's quantum indeterminacy is now accepted, and once you master a science, then you can, in later years and later centuries, we will come up with the technologies. And right now, all this scientific technologies that we have, including these communications, cell phones, computers, laptops, in the way that I'm communicating with you, they are all are on the foundations of the accuracy of quantum physics. All right, thank you very much for paying attention to this. Thank you very much for paying attention to this lecture. So for this lecture, I've taken multiple references. The reference that I actually recommend is Quantum Mechanics, Introduction to Quantum Mechanics by David J. Griffiths. He's an excellent teacher of physics, and this book is intended for the undergrad level. I've also taken these images from Wikipedia. As all of you know, Wikipedia is a free online wonderful encyclopedia, but I should warn you that not everything that is written in Wikipedia is approved scientifically. It doesn't go through the peer review process. So you must either know the methods of science, or you must be a scientist himself to tell which one is science and which one is not science. But I've taken the pictures from Wikipedia, so we're on the same side. So anyway, thank you very much for paying attention. I will come back for another lecture, and we will continue our discussion on quantum physics. So remember, the universe is meaningless. It is us that give meaning to the universe. And the best way to understand the universe is through the methods of science. Take care of yourselves, and bye-bye.